All right, so now that we looked at the scatter plots, we do need a more systematic way to decide if there actually really is a correlation there. So looking at the scatter plots is definitely the first step because you want to look at the data and see if you can visually find a pattern, right? If it looks like there's no pattern there, then you're probably not going to move on to the correlation coefficient step because it just doesn't make sense. So you're going to look at the scatter plot first. You're going to see if it seems like there appears to be a pattern. And again, in our case, we're looking for linear patterns. And if you do see one, then we're going to take it the next step and actually now do some calculations to verify there really is a correlation or relationship there. So identifying correlation using scatter plots is subjective, meaning that it kind of varies from person to person. One person may think there's a strong correlation, another one may not. So you do need something more rigorous. So a precise measure of the type and strength of a linear correlation, again, we're focusing on linear, between two variables, is to calculate what's called the correlation coefficient. Remember, coefficient is just a number. A formula for the sample correlation coefficient is given here, but it is definitely more convenient to use technology to calculate this value. So I will do one example by hand just to show you the process, but then I will show you how to use technology here, which is by far the recommended way to do this. This is also called the Pearson product moment correlation coefficient, named for the statistician Carl Pearson. So if you hear the Pearson product correlation, it's not because of our publishing company or the publishing company Pearson, it's based on the statistician. So the correlation coefficient is a measure of the strength and direction of a linear relationship between two variables. Now, the reason why it's the direction is because you will see either a positive or a negative number. Positive numbers relates to a regular increasing line. Negative numbers relate to a decreasing line, just like you would have for slope. And you also have strength here. So what happens is the symbol we use is R here. And what happens is your R value is always between -1 and 1. And what happens is the closer to 1 or -1, the stronger the relationship or correlation. So if your R value is close to 1 or -1, then you have a very strong correlation there. If your R value is around 0, then either you have no or minimal correlation. So that's how it determines the strength as well. This is the formula. Again, it's quite complicated to use. Don't forget that symbol here, the sigma, means to sum or to add. So the formula is quite hard, but the individual parts are easy. It's just very tedious. It's a lot of adding going on here and multiplying and dividing. So nothing unusual calculation-wise, but just very tedious. So we'll do that in a second. Okay, here are just some examples as well. Other thing to note, again, when there's no linear correlation, R is close to 0. It is important to remember, though, that when R is close to 0, it does not mean that there is no relation at all between X and Y, just that it is not linear. So let me clarify that here. So no or minimal linear correlation here. And again, we're talking about linear correlation in both of these cases. So here are some examples. So here you have a perfectly straight line, which in the real world is not going to happen, but it could be close to this. So a perfectly straight line is when you have perfect correlation. This is going up, so it's positive direction, and your R value would be exactly 1. Realistically, if you have a strong correlation, it's not going to be 1 exactly. It may be something like 0.81, which is close to 1. And you can see that the data is a little bit more spread out here, but you still kind of have this overall linear effect. Here is a value of 0.4. So you're kind of, again, still seeing that in general, you have this kind of linear effect going in that positive direction, but it's a lot more spread out. Here you have a perfect negative correlation. So perfectly in a straight line going downward. So your R is -1. Here is a strong negative correlation. So again, that data is going downward, but you can still see it lies pretty closely on a line here. That 0.9 is pretty close to 0.1, right? 0.9 is close to -1. Here's an example where, look at, your R is very close to 0. You have no real correlation. So I don't really see a pattern of up or pattern of down. It just kind of looks to be all spread everywhere. So you have no correlation there. Okay. Now, just one thing to note, to use a correlation coefficient to make an inference about a population, it is required that the sample pair data is random and that X and Y have a bivariate normal distribution. Now, we're not going to really worry about that here. We're going to focus on the first two sections of Chapter 9. So for now, you can assume that these requirements are met. But like with a lot of other stuff we've done, just know that there usually are requirement checks before you can proceed with a lot of these problems. All right, so let's do an example. All right, so I'm going to do this by hand first, and I will show you how to use it on technology, which of course is the recommended way to do it. So there is a really messy formula there, but what I'm going to do is actually just organize first. So we're going to use the same data from example 1, which was the data that I also put into our calculator already. And I'm going to just rewrite it for a second so that we have it. And I want to make sure I keep my data paired the correct way. So 1.8 was with 604.4. 1.3 was with 434.2. 2.4 was with 544.0. See, 1.5 was with 370.4. 3.9 is with 742.3. 2.1 is with 340.5. 0.9 is with 232.0. 1.4 is with 262.3. 3.0 is with 441.9, and 4.6 is with 1,157.7. So this was already given to us in the problem. Okay, so this was part of our original data set that we had. Now we're going to do a lot of calculations here. So this is the process of you doing it by hand. So again, this is given. The next thing we're going to calculate is we're going to do x, y, which means x times y. So you're going to multiply these values together. So you're going to do 1.8 times 604.4. And then you're going to do 1.3 times 434.2, 2.4 times 544.0, and so on down the line. And what you get for answers, I'll just give you the answers. It's 1,087.92, 564.46, 1,305.6, 555.6, 2,894.97, 715.05, 208.8, 367.22, 1,325.7, and 5,325.42. Now you're also going to calculate x squared. So you're going to go back to your x's. You're going to do 1.8 squared, 1.3 squared, 2.4 squared, and again, so on down the line. And I'll just give you the answers. It's 3.24, 1.69, 5.76, 2.25, 15.21, 4.41, 0.81, 1.96, 9, and 21.16. And you are also going to find your y squareds. So our y values here, so again, 604.4 squared, 434.2 squared, 544.0 squared, and again, all the way down the line. So these values are really large. Let's see, we have 365,299.36. You have 188,529.64. 295,936, 137,196.16. This one has no decimals, 0.0, just so to clarify. 551,009.29, 115,940.25, 53824.0, 68,801.29, 195, 275.61, and finally 1,340,269.29. So we have a lot of work right here. And again, these numbers are already done because I'm taking an example from your text. So you can see it's a lot of process, a long tedious process, but the calculations themselves are easy. You're starting with your original data, you're multiplying the data, and then you're squaring each data set. And then what you're going to do is you are going to add up all the columns. Okay. So when you add up this column, this is the sum of the x's, and you get 22.9. When you add up this column, it is the sum of the y's, and you get 5,129.7. When you add up this column, it's written like this, sum of the xy's, okay, but really you're doing the xy multiplication first, and you get 14,350.74. This is the sum of the x squared. So again, the x squared is first, and then you're summing in this case. You get 65.49. And finally, you add these all up, you get the sum of the y squareds, and you get 3,312,080.89. So that is the background work here for the formula. We haven't even used the formula yet. So what your formula is for R, it's n, which is your sample size, times the sum of the xy's, minus the sum of the x's, times the sum of the y's. And that's all over. Now you want to be careful, there are two square roots here. It's the square root of n times the sum of the x squareds minus the sum of the x's squared. So this is different. We're going to take this value here and then square it. And then you're multiplying that with another square root. So we're doing n times the sum of the y squareds minus the sum of the y's squared. Now our n here is only 10. So we have 10 data points. So I have 10 times the sum of xy is this value right here. So 14,350.74 minus the sum of the x's, which is here, 22.9, times the sum of the y's. And again, my first square root, I have 10. The sum of the x squareds is 65.49 from here. Minus, and now this means to take the x answer and square that. And then finally, again, I have 10 times the sum of the y squared. So I could try to squeeze in this really large number here. Okay, minus the sum of the y's, 5129.7, running out of room, and then that value is squared. All right, so cleaning up a little bit, I already did the calculator workout, so you can try this at home. I'll just fill in your two values. Again, you want to just simplify it a little at a time. It's really easy to make a mistake here. And after all the calculator work, again, I'm just showing a couple intermediary steps so you can kind of check your work at home, but you can try it at home. You get about 0.874. So your R value here is about 0.874. Now this is pretty close to 1, right? So this does suggest a pretty strong positive correlation. Okay. So again, the closer you are to either 1 or -1, the stronger that relationship is, the stronger the correlation is. And it's positive here because my value is positive. If you go back to the scatter plot that we made, let me see if I can find it real quick. So here is the scatter plot from that data. And we did see it look like a positive linear correlation here. So we have the scatter plot that shows that. And then we also now have our R value that also shows, yes, both of these things are showing that we have a strong positive correlation here. All right, now how do you do it the fast way? And I really hope you use technology for your homework assignments. So I strongly encourage you to do this. So one thing to do is you may have to make sure your diagnostics feature is turned on, although I'll say that I've used it without it being turned on and it has worked fine. But just to check it, the catalog button is down here. It's the 0 button. So you press second and then 0. And then if you just kind of scroll through to D for diagnostics, you just want to make sure you have diagnostic on. So I'm going to hit diagnostic on and then just hit enter. I think I already turned it on. That's probably why. Hang on, let's try it again. Okay, and you should get a little symbol on the app that will say done once it is entered. So you just hit it and then hit enter and it'll say done. If you have the actual calculator, just make sure you hit it, I think, twice to select it. Now, once you've done that, what you're going to do, and you have the directions here, is you do need to make sure your data is in L1 and L2. Now, we already did that when I showed you how to do the scatter plot. So my data is in L1 and L2 already. And then what you're going to do is you're going to press Stat Calc. And I want the one that says Lin Reg for linear regression. Be careful, not LN Reg. You want LIN, like linear. And it says A plus BX next to it on the app. So you're going to click that. Now, it has a lot of things that you can enter up top here, but you really only need to enter 2 things. You're going to enter L1. So I hit second and then the number 1 to do L1, comma, second 2, do L2, because that is telling my calculator that this is where my X and my Y values are. And then you're going to hit enter. And you will see at the bottom that R value. So careful, not R squared. You want the R value right there. And it's exactly what we got, 0.874. So this is the way that I hope you'll do it. The way I highly recommend that you do it. Now, if you don't have the app at home, I do have a link here. If you go into the actual Word handout, you can click that link and you'll see a calculator there that you can use. So let me just show you that as well. I'm going to pause the video and bring that up on my screen. Okay, so here's that website that is linked in the lecture notes here. And what you do is you'll see when you first get here, this box is going to be blank. So what I did to save some time in the video is I just entered my data already, and you entered it X comma Y. Numbers only, so you need the comma in between, but no parentheses or anything like that. And you entered it as the pair of the points. So I entered all 10 data points. Okay, and then all I did was click submit data, and you will see the correlation coefficient will come up here. So there's that same 874 that we found. And again, you can use this if you don't have the app at home or if you don't have the graphing calculator at home. Then again, please, I would highly recommend not doing this all by hand. So you can enter your data points here to get that R value instead. Now, just as another side note, I am skipping over example 5 in your text. So you can feel free to check that out on your own, just to see another example done out here. But it's going to be a very similar process. And they kind of go through different technologies that you can use. So obviously I'm focusing on the calculator, but if you prefer to use Excel and things like that, there are other technologies that you can use.